There are two special trig limits that in calculus they just expect that you kind of remember these. With a graphing calculator, you can always graph these functions and see what happens. But without a graphing calculator, if you don't just remember what it is, it's hard to get the answer because you definitely probably don't know what the graph of sine of x over x looks like by itself. Without a graphing calculator, making a chart is not going to be that feasible without a graphing calculator to help you. And so these are ones that show up sometimes, and we'll kind of come back to them over and over again. But if you have sine of x over x, you can graph that. But you can't just do direct substitution because if you plug 0 in the bottom, you have an undefined, like it's not defined at 0, but it does actually have a limit. And so I'm going to graph this one just to show you, and then I won't graph the next one. I'll just try the answer. But let's see, sine of x over x. Sine of x over x graph. And we could zoom in here. But even without zooming in, if I want to know what's happening as I get closer and closer to 0, if I come in from this side and this side, what y value does it look like that's getting closer and closer to? 1. It doesn't equal 1 at 0 because it's undefined at 0. It's just if you tried to find the value here, if you went second calc and we said, what's the value at 0, it leaves it blank because it's undefined at 0. But it is approaching 1, and that's where they're never going to give you this question when you're allowed to use a graphing calculator, because it's really easy with the graphing calculator. They want you to just memorize this and to know that the limit as x approaches 0 of sine of x over x is always going to be 1. And the same thing, we have this special cosine limit, and again, we could graph it, and we could use the graph to get our answer. The limit as x approaches 0 of 1 minus cosine x over x. And if we graph it, I'm not going to though to save time here, it's going to equal 0. It's not defined there, but it does equal 0. So you're going to see some of the ones that I originally had on the homework from yesterday, but I took off because I knew we wouldn't get to this. They're going to give you some variations of this. So instead of just giving you what is the limit as x approaches 0 of sine of x over x, they're going to give you something more like this. Yeah. Actually, I don't know if I had this number right now. And so you have to do a little bit of algebra here. You might get lucky and maybe just guess what the right answer is, but I'm going to show you why this works. This does not look exactly like this. Do you agree with that? Because to use this, we could kind of put a U here if we wanted to. To use this rule, whatever sign is, sign of whatever, it has to be the same number on the bottom. All right, so you can't just do that with anything. The other thing that you can't do is many people, when I say, what could we do here, they say we could factor a 10 out. If you're taking the sine of something, like this is the sine of 10x, you can't separate that and pull that 10 out front. Do you agree with that? Like the sine of 2 pi, you can't pull the 2 out front and then just take the sine of pi and it works out, right? This is an angle, so you can't separate that. What we can do is this is a fraction, and we can do some algebra here. In order to use this, I need to have 10x here, then there needs to be a 10x on the bottom. So can I just multiply the bottom by 10? If I multiply the bottom by 10, what else do I have to multiply by 10? The top. And so I'm going to write the 10, well, I'm going to rewrite it next to it because I don't. What if I multiply the bottom by 10 and the top by 10? Have I kept that to be an equivalent expression? Yeah, because if I cross the 10s out, I'd be back to where I started. So the idea is you want to make those match up. And now, if I wanted to separate this part, I could say, let's take the limit as x approaches 0 of 10 times the sine of 10x over 10x. And tell me if you don't agree, like this is the same thing as this. I just kind of separated the 10 out in front of it. But it's still the same thing. Yeah, it's still at the top. It's still 10 times all this. I just separated it because this is our special limit, right? If you have the sign of some u value and that same u value on the bottom, and the limit as x goes to 0, what is this always going to equal? 1. Like, even though there's a 10 here, as long as this, so maybe it helps if you put a u here, I don't know. Sine of any u value over u is going to equal 1. So this is just 1, and 10 times 1 is 10. People usually say, I could have probably guessed that it was 10 based on the fact there was a 10 in front of it. But sometimes there might be a number on the bottom and you need to factor it out. So you need to make sure you look at what's there and how do you get that to match up. Okay, this doesn't show up a lot, but it's definitely in this chapter, and so I want you to be aware of it. And I gave you 2 or 3 problems today using these trig ones. Okay? What else? Properties of limits. I was helping students with pre-calculus, and Parker comes behind me, like I'm sitting on top of the desk helping students. Parker comes behind me and just does this to the back of my head. And like it went on for like 3 or 4 times, and finally I was like, will you please stop? I don't know how massage Tucker thinks here and doesn't lose her mind because I already losing my mind on the second day of school. Well, her kids seem to be much better behaved than mine. I know. Maybe it's because they have each other to entertain. I don't know, but
They seem hot together in January.
I know. She finds out, I think, next month what she's having.
Who?
Mrs. Scott.
At the taste of self button, and I was like, everyone was like, oh, I'm so sad. And I was like, so how long is this going to take? And she goes, about 9 months. I was like, I meant when are you due?
So, notice that we have the limit as x approaches some number of f of x equals some number L. And if you have the limit as x approaches the same number of a different function equals, and we're just using k to equal another number, there are certain properties that hold true, which means that we don't necessarily have to have a function. If you know these properties, you can just work them out. And so some of these are pretty much just the same rule as most algebra rules. The scalar multiple property says that if you take some number and multiply it by the function, then that's the same as taking that number and just multiplying it by the limit. Or the limit value. So let's say the limit was 7, and then you took that function times 2, you would just take the limit times 2 and you could get 14. And this is where on your homework you're going to see, we'll do an example in a minute, they're not going to give you the function, they're not going to give you a graph, they're just going to tell you the limit of f of x equals 2 and the limit of g of x equals 3. Do these problems, and if you know these properties, then they're pretty simple to do. But you would just multiply. But yes, L stands for the limit value. We can also add and subtract limits. Again, notice the big thing is the limit is approaching the same number. If for some reason we had one limit approaching 2 and one limit approaching 3, these rules do not hold true. But if you're taking the limit as x approaches the same number of f of x plus or minus g of x, then it's just the same as taking the limit values plus or minus each other. So that would be the same as taking L, which is the limit of f of x, plus or minus the limit of k. It's probably kind of catching on here. I'm going to show you 2 at a time now. The same thing holds true if you multiply or divide the functions as you're taking the limit. So the limit of x as x approaches c of f of x times g of x is the same as taking the limits times each other. So that's just the same as taking L times K. So you can probably guess that the division one is just going to be dividing those two limits, and it is exactly, it would just be L divided by K. That's my last one of these. The power limit, if you take the limit as x approaches a number of a function to a power, it's the same as taking the limit to that power. And we kind of did that property yesterday. We just wrote it a different way. So part of your homework today, they're going to give you some information. Again, not giving you an actual function to work with or a graph. And you just get to use these properties, which again, if you know the properties, they're not that bad to do. So let's look at a couple of those real quick. There we go. I just did one. So this one says, if the limit of as x approaches c of f of x equals 4, then find these values. And so we don't know what f of x is, but we know that the limit is 4, and so we can use these properties and still get numerical answers, even though we don't really know what value is approaching to c, and we don't know what the function itself is. So I'm just going to replace the function with what the limit equals, right? So that's just the same as saying 4 to the third, and 4 to the third is 64, not 12. So what about for part B? What are you going to do? Yeah. F of x is just, oh, you have a 1/2 power? Yeah, that works. We could do f of x to 1/2 power, right? Because technically, it doesn't say we could just take the square root of it. And then we can just plug 4 in there. And that would just be 2, right? Well, you could, because the square root is the same as the 1/2 power, right? So it does still work. That's right, I like it. Alright, so okay with that? Some of them, I think the one on your homework actually gives you a f of x and a g of x value, so just pay attention to which one you're using. And some other ones, but I'd like to get to our theorem today. I should have brought you sandwiches today, because today we're going to learn the sandwich theorem. I don't know. Cheap ones. Alright, so it's called the squeeze theorem, but most calculus people call it the sandwich theorem. It's up to you if you want to write this out or not. I think it's important to write out, but if you want to just wait and write down the bottom part, the actual theorem part. But sometimes you can't find an actual limit, right? And that's what it says. If we cannot find the limit directly, we may be able to find it indirectly with the sandwich theorem. Because the theorem refers to a function whose values are sandwiched between two other functions. Or the other reason it's called the squeeze theorem is you have one function that you can kind of put in between two other functions, so you can think about squeezing it in between the two. But it's easier to think about a function is sandwiched in between the other two. And I have a little metaphor for you about a sandwich, like a bologna sandwich. This is our last thing we're learning today, is the sandwich theorem, and we're going to do an example of it. here's the actual theorem, and then we're going to, oh look, I drew a picture here, so, all right, I'll just let you write it, and then I'll draw my picture. So that way you don't have to write and listen at the same time, because I will look at you in school. You know what I should do? I should pause my video while we just sit here and write. Okay, I'm going to draw a picture here to kind of show you what this is saying. But it says if G and H have the same limit as x approaches some C value, then F has that limit too. Only if F is squeezed or sandwiched in between these two. So F has to be bigger than G of X, but smaller than H of X. So it doesn't have to be exactly like this, but it's important that H of X is your top function. So I'm going to make some function here, and I'm going to call that H of X. And then my bottom function is going to be G of X. Okay, that's just kidding. I should make that better. That's G of X. And then F of X is going to be sandwiched in between there. And notice I made these pretty close together because I'm going to try to make F of X go right in between there. That's nasty. And this would be my C value. Yeah, because they're all going to have the same limit.
No, I didn't know there was.
Sorry. Just cross it out and start again. You can't erase it these days. Here's why they're supposed to touch. It doesn't work for just any two functions in between, like outside another function. Those two outer functions have to have the same limit, which means they have to have the same y value at that point. So that's why they have to touch at that same c value. And then if f of x is fixed right in between those two functions, then it's also going to have the same value. So it says if the limit as x approaches c of g of x, that's the bottom function, has the same limit as h of x, which happens to be L, then the limit of f of x will also equal L. And this is kind of the best. I like this theorem because it's good practice on writing like a summary of proving something kind of. If this and this is true, then this is also true. Not only proofs, you're going to be able to write your answers nicely. I mean like be able to use words to explain your answers. So let's look at one with actual real numbers in it and see if we can make sense of it before the elements. Are you okay with me moving on with this? Today is Thursday, but it's probably time afternoon, so your afternoon class will be shorter, not this morning. You can just, don't even write or find limit graphically. Use the sandwich theorem to confirm your answer. Let's just practice using the sandwich theorem, because I trust if I told you to graph this and find the limit, then you can do that. What if you didn't have a calculator? That's where the sandwich theorem comes in handy. And I picked one here that's pretty easy. Most of the time, the sandwich theorem is used when you can't take the limit. Like on this one, do you agree that I could just plug 0 in there and find the limit? But what if it was like divided by something weird? Like sometimes there wouldn't be a way to take the limit algebraically. And so we're going to actually use the sandwich theorem, even though we don't have to on this one. So here's the big thing on the sandwich theorem. You have to find the two outside functions. And so usually they give you trig functions to deal with because, can you tell me, so there's an x in front of that, what is sine of x restricted between on the y-axis? What's the biggest and the smallest it's ever going to be? 1 and -1, right? Agree with that? So the big thing on the sandwich theorem is you have to find the outside functions. So on this one, I can say that x sine of x is, well, hold on. I could say that sine of x is sandwiched between -1 right? We know that. But what about that x in there? What do I have to do about it? I can't just put it in there. I have to like make it equal to do that. So what could I do? If I want to put an x, right, so if I put an x in here, then I have to put an x out here and out here to keep it all balanced. Follow me on that? So that would make this negative x is less than or equal sine of x, sorry, x sine of x, which is less than or equal to x. So you have to take the trig function that you know is bounded between -1 and 1, and then do whatever you need to do to make it equal the actual function. Sometimes you might have to divide by x. And again, I picked the easy one. I should have picked a fraction here, but that's okay. So what we've done is we've sandwiched this function in between two easier functions on the outside. So now what you want to do is let's take the limit of the two outer functions. So I'm going to take the limit as x approaches 0 of negative x. Do you agree that that's a pretty easy function to take the limit of? And what would the limit as x approaches 0 of negative x be? Just plug 0 in, and we would get 0. And I'm going to take the other bread of the sandwich. Right? This is the meat of the sandwich. Outside is the bread. Take the limit of this side. The limit as x approaches 0 of positive x is going to be 0. If you can show that the two outer pieces of if the two outside functions are the same, then by the sandwich theorem, we can say that this limit also equals 0 without ever finding it. So how would you write this on your paper? I would write, because the limit as x approaches 0 of negative x is equal to the limit as x approaches 0 of x, which happens to equal 0. Right? So that's kind of the if part. Because this is true, then by the sandwich theorem or the squeeze theorem, I'm going to say by the sandwich theorem, well, you probably should write it out because I don't think AP graders know that ST means sandwich theorem. By the sandwich theorem, the limit as x approaches 0 of x sine of x also is going to equal 0. So notice you don't have to write a paragraph, but you have to say, because this and this is true, then the sandwich theorem says that this is also true. And I think there's one on your homework, and we can talk about it tomorrow. Probably there's going to be one on the test that we have over this chapter. It's not a huge part of calculus, but it's kind of some good practice at dealing with theorems and doing a little bit of algebra there. Oh yeah, you're right. Sorry. I know, that's bad. I was running out of room and I was trying to fit it on there. So someone at a calculus conference gave me this next little thing. You don't have to write this down, but it says that here's a real life application, because one of their students asked what's the real life application of the sandwich theorem, and it says the slice of bologna is constrained to lie between the bottom slice of bread and the top slice of bread. If both the bottom and the top slice head for your mouth, so does the bologna. You can't escape. So hence the other name for this theorem, the sandwich theorem. Because someone in his class said, what's a real life application of the squeeze theorem? And there's really not a real life application. But you take the bread to your mouth and the bologna's in between it, the bologna's going to. So if you take the limit of two functions, the function in between is not going to your mouth, I guess, but the limit's going to be the same.
I love how relatable that is.
We can't relate it to real things, right?
Eventually we can, but not this. Eventually we can do some really cool stuff with calculus, but it takes us until about March or April to get there.
Why do we
Because we have to lay the foundation. These 6 problems you're going to do, I'm calling this day 2, because I'm going to rename that. I fit 2 days on day 1. I know that's really confusing, but the same page, I have an assignment sheet for you if I can find it here. That's stuff for drawings.
You know, it's really bad if you just
Page 66 to 68. I was grading some quizzes in assignment sheet, I just broke this up into 3 days because I'm assuming that you did 2 and 3 and yesterday's homework on the same day. 66 through 68. Alright, so we'll wrap up 2-1 tomorrow. We'll start talking about the true definition of a limit.